You know, I had multiple people ask me under the comments, under some of my videos, when will the next machine learning episode come out? Okay, not multiple people, one person asked me that, but you know, one person being interested in something is one too many that I could wish for ever. So basically, they asked me, why do you not film the machine learning experience anymore? And the truth is because I think that there's too much information that my brain is extremely undeveloped in order to understand these concepts. But I think that we can, oh, here we are already, that I can at least do my best in order to understand this and to learn more about this. The first thing here is the ROC curve. The ROC curve, or the receiving operating characteristic curve, is used with binary classifiers. It's very similar to the precision/recall curve, but it plots for the true positive rate and the false positive rate. So first of all, a binary classifier is a model that answers a yes or no question. It tries to separate data into only two classes, positive class and negative class. So is it a 5, not, or is it not a 5? Then we have 4 concepts that I already mentioned, but I just want to remind myself of them. I can have concepts from the model, predictions that can be positive or negative. And I can have actual positive and negative predictions and predicted negative and positive predictions. So if the actual value is negative and the prediction set it to negative, then it's a true negative value. Otherwise, if the value is actually positive and it's predicted positive, it's a true positive value. But now we come to these other two values. In cases in which the actual is a negative, but it's predicted positively, it's a false positive. And if it's actually positive and predicted negative, it's a false negative prediction. An example, if a person has fever and the model correctly says so, then we are talking about a, wait, maybe I have it here somewhere. Then we are talking about a true positive value. If a person is healthy, but the model says they have fever, then it's a false alarm, it's a false positive value. False negative value is a person is sick, but the model says they're fine. No. Let me just open my... I'm just reminding myself here. I still haven't done anything yet. Let me take this other color. So what is the false positive value? Or false positive rate? False... what size is this guy? Positive rate. I'm dividing false positives plus true negatives over false positives. And also I have the true positive rate, which divides true positives over true positives plus true negatives. So maybe I should have written them in another order, but doesn't matter. Also. So the true positive rate. Out of this many positive cases, how many did we correctly catch? Let's say 100 people are sick. And our model caught 90 of them. So what do we have? We have true positive it's 90. Over true positives, it's 90 plus 10. It's 90 over 100. It's 0.9. This is our true positive rate. On another hand, we have the false positive rate. It tells us out of the actual negative cases, how many have been correctly labeled as positive. So we're going to do another example. Let's say we have 100 healthy people, but we have a model that flags 10 people as being sick incorrectly. So the false positive rate is 10 over true negatives are 90 plus 10, and it's 0.1. I mean, this is simple. This is relatively simple. It's not something that I will remember on my own, but if I get reminded of, I will say to myself, so this is this concept, maybe I can use it in something. Let's run the code. Pretty quick. So this imports here it is. So let me try to remind myself what each of these values are. So y train 5 it's a vector of true and false values, right? So it's going to be true if the digit is 5 and false if it's not 5. And scores what are scores? Scores are how confident the model was for each sample. So if I do here, maybe I can run this again. Where are you? Here. So if I do print y train 5 and print y scores, I just want to make, I didn't do, every time when I come back to machine learning after a long time, I have no idea what each of this is. So these are the scores for how confident the model is. And now here we're gonna draw it. But what this method does internally. So can I open this? Maybe I can. Is there some logic here? So this is the model. Attempts to drop threshold corresponding to points in between and collinear with other points. All right, let's not read this. Basically, it goes to a range of thresholds, and at each threshold it says, okay, consider every score above this threshold as true, which is predict 5. Then calculates how many of these predictions are true positives and false positives, and then it tracks how TPR and VPR change on the threshold range. Interesting. So what do I have here? Again, let me go back. What do I have here? Let's say I have my values, and then I have a list of thresholds. For example, our decision score cutoffs, they can be 6,000.2 minus 13,250. I don't know why am I going 10 stars. Minus 2, 5, 2, 5, and so on. So these are the decision score cutoffs for the model tested. And each threshold corresponds to a point in the FPR and TPR lists. And then we say, okay, what if we only call it a 5? The model score is about, I don't know, let's say 3000. What if I call it 5 only in this case? And this basically, this method calculates just that. It seems really simple theoretically. And here we have a graph. Let me try to understand the graph, please. So this is a curve. This, wait. Let me remove this. This is the curve right here, the ROC curve. So it shows us how our classifier balances catching positives versus raising false alarms, mistaking non-5s as 5s. We have the x-axis, which is the false positive rate or the fallout, which says, okay, how often the model makes a mistake on something that's not a 5. If it's on the left, it has few false alarms. If it's on the right, it has a lot of false alarms. Then I have the y-axis, which tells me how well the model catches actual 5s, true positive rate. So it's the amount of true positive values. If I have 9 divided by, I don't know, if I have 10 in total, it would be 90%. So this is how well the model catches actual 5s. If it's on the bottom, it catches few. If it's on the top, it catches most of them. Now, the blue line is the ROC curve. This line tells us how recall and false alarms change as we move the threshold. So on the left side, we have a very high threshold, which means that the model only says 5 and it's super confident. It's high prediction, but misses many 5s. And on the right side is very low threshold model. Model says 5 a lot, even when unsure. High recall, but also high false alarms. So the next thing here is the ROC aux score. God, this is already getting too confusing. So it's the area under the curve. A perfect classifier will have ROC aux equal to 1, but a random one will have it equal to 0.5. And our value is all right. The following cell might take a few minutes to run. It didn't because I upgraded my RAM, so it's almost instant. So this is a random forest classifier. Or maybe this is the cell that takes a lot of time, it seems. Wait, let me just explain what is happening here. From the moment we import the random forest classifier to the moment we run this line of code, which is confusing, but let's start. Let's give it our best in order to understand this. I have a random forest classifier. I'm training a random forest classifier to detect if an image is a 5 or not a 5. And I want to see how confident random forest classifier is for each prediction. first line of code here. I'm creating a random forest model. This model, under the hood, builds many decision trees and takes a majority vote. So this is the implementation. I'm gonna probably look at it later, but wait. And it's often more accurate than simpler models like SGD. The random state makes sure we get the same result every time we run the code for reproducibility. We are using the cross-val predict method. It does the threefold cross-validation. It splits the data into 3 chunks. And then trains on 2, tests on 1, then rotates. So each sample gets a prediction from a model that never saw it before. This method property will return probabilities instead of predictions like true or false. So for each image, we would get something like 0.02, something like this. 0.02, 0.98. 2% chance it's not 5, 98% chance it is a 5. And now here, we print the first 2 rows of probabilities. Like here. The first one is 89% 5, the second one is 99% not 5. It's very confident that it's not a 5. And these are estimated probabilities. Among the images that the model classifies as positive, they're actually about 94. All right. Now what do we have here? Let's try to decode this as well. Globally, in a global picture, this snippet will find all samples where the model says, I am 50 to 60% sure this is a 5. And then it checks how often was the model actually right in that range. This tells us how good the model is calibrated. So when it says, okay, I'm 60% sure, is it actually right 60% of time? This is our probability array. And this will grab the second column of the probability array, this piece of code right here. So it's gonna be 89%, 0.01%, etc., etc. Which means that each value is the model's confidence that this is that this is sample is 5. Now here we do the same thing. And we have 2 conditions. One of them checks whether, where's my pen? One of them checks whether the prediction is greater than 0.5, and the second one checks if it's less than 0.6. So we want to check whether the samples, whether the model was more than 50% sure but less than 60% sure. So it's kinda sure, not super confident. So if we have values like, let's say, let me print this maybe. Print, what should I print? Print this. And run this. And now I'm having this whole array for myself. So I'm checking, okay, is it bigger than 0.5 or is it less? And is it less than 0.6? So now looking at these values, what will I have? This will be false, 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 top, 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 false, false, false. And if I print IDX 50 to 60, false, 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 false. And then I look right here. If I print Y train 5, so these are the real values. So this is masking. That's why I don't understand, because these are NumPy arrays. I don't hate NumPy arrays. They're really useful. But I didn't understood this because I thought, okay, both of these are the same length. How is he filtering based on this? And basically what it does, and the thing that I realized and understood just now, is that, for example, let's say Y test is an array in which I have NumPy array true, false, true, false, true. MP, do I have MP somewhere? I should have MP somewhere. Import MP, MP, MP array, here it is. MP random seed, where do I need to import NumPy SMP? All right, maybe I just didn't run this cell, no idea. It comes afterwards. I'm so smart. I'm not smart, I'm an idiot. I'm trying to do this beforehand. Okay, so this is the Y test. And then let's say I have these 50, 60 test. It's gonna be NumPy array false, true, false, true, true. And if I do what? 50, 60 test, what? Why 50 variables in Python can start with a number? I just realized that. It is going to be Y 50, 60 test. And if I run this, array, it's not a prey, man. It's not a prey, it's array. Please. False, false, true. So it creates a mask which will return only the values where the mask is true. So it's gonna be false because the mask is true, false because the mask is true here, and true because the mask is true here as well. So I have here the first item, which is actually not a 5. This one, which is also not a 5, and this one, which is true. And then if I sum them, I'm gonna have only one. In this certain scenario, I'm gonna have only one because only one of these values was true. So the model guessed maybe a 5 in 3 places, and it was right once. And now I compare it to this, which is the total number of predictions in that range, and I get 33%. And this one has 94% accuracy in that range. So what this means, it says among all the samples where the model said I'm 50 to 60% sure this is a 5, it was actually correct in 94% times. Which means, wait, I'm only 50, 60% sure, but I'm right 94% of time. Isn't that telling us something important? Yeah, that the model is underconfident in that range. It says, yeah, I was right 94% of time, even though I'm not sure that I'm right 90% of time. Which means that our model is probably much more accurate than its probability says, giving us probabilities when it's actually right most of the time and possibly badly calibrated. This code right here calculates the data needed to plot a precision recall curve for our random forest model. So we have all of our data, we have scores. This will extract just the probability of it being a 5 from our earlier cross-validation result. Then we are calling the precision recall curve, which will sweep through many threshold values. At each threshold, it will say, okay, that treat every sample above this threshold as a 5. Then it will calculate the precision and the recall. Again, precision of the samples we predicted as 5s, how many were actually 5s, and recall of all the actual 5s, how many did we catch? And it returns an array of precision forest, recall forest, and threshold forest. And here we just plot this, and maybe I can also do a tiny example of it. Let's do it like this way. We are here. So let's say our y scores after getting them out of the probabilities are, let's say 0.9, 0.2, let's say 0.6, let's say 0.8, and then we have our real values, which are, I don't know, true, false, true, 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 false, true, true. So if it's at a threshold of let's say 0.5, what do we have? We have our first value, which is predicted as true, the second and the third. These are the prediction samples. So what we will have as a true prediction will be true positives are 2 and false positive is 1. Which means that our precision is 2 true positives or 3 total. It's going to be 0.67. How many false negatives do we have? None. So recall will be 3 over 3 is going to be 1. And then I think increase the threshold as well. So this is what it means. Okay. This is the graph. I'm not interested in graph anymore. So we could, what does it say here? We could use to compute, all right. This value, this is this. Oh, and the next subchapter is multi-class classification. So if you are interested in this serial, please let me know if you want to see more machine learning videos from me. I could maybe find a book that's more understandable both for me and for us. I'll finish this chapter. I really want to finish this chapter. I'm also not a quitter. But if you want to see something else or another book that you want me to go over through and rehearse and prepare and work with it, please let me know. Thank you.